All right, in this next lecture segment, we're going to talk about the differences between the ideal gas law and real gases. We've talked all about the ideal gas law, how great it is, with occasionally mentioning, well, you know, it's almost true. And so we're going to interrogate those differences between real gases and the ideal gas law a little bit more and learn how you can start to correct for it. If you take a later chemical engineering class in mass and energy balances, then you'll dive into several different ways to compensate for these things. If you're dealing with like supercritical fluids, then obviously the ideal gas law breaks down. So the lecture, but we're going to start with the basics here. So we are going to, as the lecture objectives say here, we're going to understand and quantify the differences between the ideal gas law and real gases. So the first thing to remember is that the volume of a real gas is larger than that predicted by the ideal gas law, because it's the total volume that the gases have to move around, the molecules have to move around in, plus the volume of the molecules themselves. Now, at lower pressure, the volume of the gas particles is negligible compared to the total volume. The volume that the molecules themselves are taking up is a very small fraction. But at higher pressure, then the volume of the gas particles does start to become more significant compared to the total volume. As a result, the volume of the real gas at high pressure is somewhat larger than the ideal value, because it's the volume of the gas, the volume between the molecules, but also the volume of the molecules. Another way to think about it that sometimes can be easier for some people is to think that for any given molecule moving around, given a container size, then the amount of room you have to move around in is slightly less, because you can't move into a place that's occupied by another molecule. Okay, so that's one big factor. The attractive forces between particles become more important at higher pressures. That's the other factor. Real molecules have electron clouds, and those electron clouds interact with each other, usually providing an attractive force, unless you're right smack dab on top of each other. So there's this attraction to molecules pulling them together. At high densities, the molecules are closer and thus can attract each other more. If you've got a really dilute box, then they don't spend that much time near each other. You know, all these interactions die off fairly rapidly with distance, so they're hardly ever interacting with each other. But at higher densities, then they spend more of their time closer to each other and they attract each other more. So those are the two components that you want to think about. So once you get to high densities, higher pressures and low temperatures, gases behave less ideally and more like real gases. And the way we compensate for these two effects, the simplest way to do this is the van der Waals equation that was derived by a very smart grad student back about 100 years ago. And you need two factors here. A correction for intermolecular attractions, and B, a correction for molecular volume. So this is what it looks like. That the volume is, rather than using the exact volume, the volume of the container, it's your volume, it's an effective volume, volume minus the volume that's taken up by the molecules themselves, which will be proportional to the molecules. And it will be, B has units of liters per mole. And then you also have a contribution for the pressure. So it's a little less clear in the version above, but if you solve this for the pressure, it might become a little clearer here. You can see that the pressure, it's nRT divided by V minus NB. The effective volume is slightly larger, slightly smaller than the real volume, so the pressure is going to be higher for a real gas according to that term. But then also the pressure is decreased by the molecules attracting each other. So molecules have a bit of volume, which therefore increases the pressure for real gases. But then they also, the pressure is reduced because molecules attract each other. And that attraction is not affected by the temperature. It's the same, the attraction just depends on the density, not the temperature. And the units of A here will be in the units, A will have units, you know, A has atmospheres, liters squared over moles squared. With those units, then the units cancel out and you get the A times N squared over V squared is proportional to the pressure, has units of pressure. And when you think about the n squared, v squared, the way to think about it is that the total amount of interaction energy has to, for each molecule, the total amount of attraction energy with the other molecules is proportional to the density. The denser it is, the more they are. But then there's an additional factor of the density, because the total energy of all the molecules together is going to be a product of the energy of one molecule, which is proportional to the density of the molecules around it, times the number of molecules, which will be proportional to the density. So it's the density squared. You can see that the molar density squared is what that's proportional to. So that increases quadratically.